Hello everyone, in this video we're going to go in section 8.1 about the arc length of a curve. So similar as the measure of area, sometimes it's difficult to know the length of a curve. So the approach that we're going to take to calculating will be the same as area. We're going to take in, for a function, we're in a given interval, we're going to take that interval and we're going to divide the interval where the curve lies, and we're going to find the length of the curve on each of those individual sub-pieces of the curve. So something like this. For example, we have this curve over here. So we've got to break apart the interval AB in many sub-intervals xi minus 1. Now, once that we when we have all the sub-intervals, then we can go ahead and just calculate the measure of the length of the line P0 to P1. And that is going to approximate one piece, then P1 to P2, and it's going to approximate the next piece, P2 to P3, and so on and so forth. And each of the pieces of the line is going to approximate the length of the curve. Of course, the closest that is going to be the curve, the less error or less difference is going to have the length of that particular piece. So as you can notice, we're doing pretty much the same that we did for the construction of the integral. So now, in this way, we calculate first the length of each of the polygonal paths that we get. And of course, thankfully, this is going to get much more easier to give me the length of the curve once that we divide more and more. So now, if we consider the difference between 2 points pi and pi minus 1, and we consider delta of yi as the difference of the points yi and yi minus 1. Then I can take two of those points in the curve with the natural two-dimensional distance. So the Cartesian distance. So this is xi minus 1 squared plus y1 minus 1 squared, and the square root of all that. We can also see this in delta notation as the square root of delta xi plus delta xyi square. Now, if we apply the mean value theorem on the interval xi to xi minus 1 to xi, there's bound to be some xi asterisk where we can see this as the difference in the y's, which is going to be essentially the difference on 2 points evaluated on the function, so f of xi minus f of xi minus 1. I can see that as certain, as f prime evaluated in that point xi star times xi minus 1 minus xi. So essentially I can see delta yi as f prime of xi star times delta xi star. And so because we have this relationship, then we can replace in here. And now we can have something that only depends of delta xi and of course f prime of xi star. So at the end, I'm going to have the difference or the distance between 2 points pi minus 1 minus pi can be put in terms of the square root of 1 plus f prime of xi star x squared, and then times delta x. Now, because we're doing the same steps that we do when we do integration, then what we do is we're going to assume that we're dividing a lot. And so when we're taking distance, we're taking really distance between points that are very, very close. And then we take the limit and the amount of partitions that we're going to make in the interval AB. So here we're making the number of partitions go to infinity. And that means that when we do that, that's going to provide me with an integral. So this calculation of all the arc length of the curve is going to end up being the integral of a to v of the square root of 1 plus f prime of x squared dx. And so that's essentially the construction of the formula for the arc length. Now, there are a couple of things that can come from here. Of course, the first is going to be the definition of the arc length. And it's going to be if f is continuous in an interval AB, then the length of the curve y equals f of x is measured by L equals integral of a to b square root of 1 plus f prime squared dx. Now, of course, this will be useful to have a function that measures the arc length as well from a particular starting point to any other point on the curve. So what I can do now is I can also replace, instead of having just go to up to b, I can calculate the arc length to any particular point x that is inside of the interval ab. So I can consider the points a f of a up to the point x f of x, and then I can define something that is the function of arc length. And the function s of x of our length is the integral from a to the point x of a square root of 1 plus f prime of t squared dt. Now, of course, you can also consider this in the case when it's not a function y equals f of x, but it's a function x equals, let's say, g of y. And it's going to function in the same way. Just replace f by g and replace the variable x by the variable y and replace the interval where the function is moving. Okay, so now that we have that, let's see some examples of that. So first, we have find the arc length of the function, and we have the relationship y equals x cubed between the points 1, 1 and 4, 8. Okay, so I'm going to calculate this in terms of y in terms of x. I'm actually going to just simplify this and say, well, y is equals 3/2. Since I'm moving in positive numbers, I'm going to assume that this is not the negative one, since this is the point that I'm using, 1, 1, and 4, 8. If I were to be using negative numbers, then maybe instead of taking the positive square root, I will be using the negative square root. Now, if we have that y is equals x to the 3/2, then the y dx, or y prime, if you will, is 3/2 x to the 3/2 minus 1, so 1 to the 1/2, and so this is going to be my y prime. Now the formula of the arc length is going to be the integral from, and because we're moving in x from 1 to 4, of the square root of 1 plus, and then I can put here y prime square dx. Now replacing what that is, remember y prime is just the y dx, and this is a form of simplifying everything, or my notation. Now this will be 3/2 of x to the 1/2 x squared. And so that is going to be integral from 1 to 4 of 1 plus, and then x to the 1/2 is going to cancel with the square, so it's going to be an x, and this is going to become 9 over 4, 9 over 4x, and then dx. This here is a very simple integral with the substitution. The substitution is 1 plus 9 over 4x, and so the du, of course, is 9 over 4 dx. So if we're replacing this, this is just going to be 4 over 9, the integral of a square root of u du. And we're going to forget about the limit of integration by a second, but we'll come back to them. So now this is 4 over 9, and then this is u to the 3/2 over 3/2. And so of course plus c, and so this is equals to 4 over 9, 1 plus 9 over 4x to the 3/2 over 3/2. And now we're gonna go back to the original points of integration, plus c if you will, but that plus c is gonna go once that we make this difference here. So now I get to plug in 4, and I'm going to simplify this to bit. So this is 8 over 27. 4 over 9 over 3 halves is 8 over 27. And then if I plug on 4 first, when I plug on 4 here, I'm going to get 10. So this is going to be 10 to the 3 halves minus, and then if I plug on 1 here, I'm going to get 13 over 4. Okay, and so we finally need to compute this number. So at this point, you can probably approximate using calculator or whatever you want. Okay. So in this scenario, we can probably use Desmos for it. So we calculate 8 over 27 times, and so 10 power to the 3 divided by 2, and then minus 13 divided by 4 power to the 3 over 2. Just recognizing this as a list. Okay, so this is 7.633. And the good thing about knowing that this is a positive number is that we actually know that this is a length. If I get a negative number, something is wrong or something went wrong in the integration. Okay, so now let's go to number 2. We're going to check y equals x squared between 0 and 1. So let's see if we can actually manage to do that. Y equals x squared between 0 and 1. There's nothing to do here special. Y prime is going to be 2x. And so the length, the arc length is going to be integral from 0 to 1 plus y prime squared, which is going to be 2x squared, the x. And so that's going to be 0 to 1 plus 4x squared dx. And so this integral is a trigonometric substitution type of integral. And here I can factor the 4, and so if I factor the 4, I'm going to get a 2 out, and then this is going to give me 1 over 4 plus x squared. And so you can kind of see here what the substitution is. X is going to be 1/2 tangent of theta, because of course x squared is going to be 1 over 4 tangent of theta. The dx is going to be 1/2 secant square. And so I get to change this. I'm going to forget about the limit of integration for a second. And then this is going to be 1 over 4 tangent square plus 1. And we're going to have a secant square here. And we have a 1/2 coming out of this, and we have another 1/2 coming out of this, so 1 over 4. But we have a 2 here, so twice, so 2 over 4. Okay, and tangent square of plus 1, it was secant square, but with the square root of secant, so this is going to be secant cube of theta, the theta. Okay. And so now this gets to be a fairly complex integral in here. Remember, when we're doing a trigonometric integral, one of the things that we want to do is we want to do some sort of separations that can help us manage sans serif substitution. So if I can just go ahead and say, well, maybe then I can do secant by secant square. Then I can try and do something, but here the substitution will have to be a tangent. So instead, what I'm going to do is I'm going to do parts in here. I'm going to assume that the v is secant square of theta the theta, because this is easy to integrate. V is tangent, and so and then I pick u equals secant of theta, and so that the u is secant of theta tangent of theta. Now this here becomes an integral by parts, and this is 1/2 u times b, so secant by tangent of theta minus the integral of b du, which is going to be secant by tangent square. And so notice that this is one of those, we're going to reach one of those possible integrals where we have the same thing. Notice that tangent square can be seen as secant square minus 1. So 1/2 secant cube is equals to 1/2 secant theta tangent theta minus, and then here we can see this as secant secant of theta times secant square minus 1 the theta. And so notice that this is really minus the secant cube integral and plus the integral of secant of theta. And so this is 1/2 secant of theta tangent of theta. Now because we still have that this is 1/2 secant cube, then we can move this minus secant to the other side, and we're going to have now 3/2 of the integral of secant cube of theta to theta is equals to 1/2 secant of theta tangent of theta, and then plus the integral of secant, that if you remember, this is the log of secant of theta plus tangent of theta. So finally we reach the integral. So this went on pretty long. Now we gotta go back to the original variable. So because we were having this, this is 1/2 secant of theta. This is where we got here to this point. Then we can say that secant cube of theta to theta is equals to 2/3. So this is going to be 3 secant of theta tangent of theta plus 2/3 of the log of secant plus tangent. Now, getting back to the original variable, notice that the original variable was x equals 1/2 tangent of theta. So if we have 2x, is going to be equals tangent of theta, right? So we can have x 2x is equals tangent of theta. And so we can see this as 2x over 1, and the triangle will be opposite over adjacent. And so, of course, this is going to be 1 plus 4x squared. And so we need the secant, so we need the cosine. So secant of theta is 1 over cosine. And the cosine is adjacent over the hypotenuse. So 1 over cosine will be just 1 plus 4x squared. So now we have all things. Tangent to x and secant is this. So this will be 3 times secant. So 1 plus 4x squared. And then times 2x plus 2/3 log of square root of 1 plus 4x squared plus 2x. So this was very exhausting, but now at this point we can go back to the original variable that we're going to have here. And so this gets to be plugged between 0 and 1, and that's going to provide me with the arc length. So in this case, we have that this is 3 square root of 5 times 2. So this is going to be 6 square root of 5 plus 2/3 of log of a square root of 5 plus 2. And then now minus, and then we plug in 0 here, and then this is 0, this first part, and this one here also becomes a 0 here, and this becomes a log of 1, so this is a 0 here too as well. And c minus c is here. So this is going to be my final result, and that's going to be the measure of the arc length. So this was a especially long integral case. Now let's see last one with x equals the square root of y, because we can essentially do the same thing with functions that are in terms of y as well. So if x is in x squared of y, square root of y between 0 and 4, then we have that the arc length is just going to be between 0 and 4 of 1 plus, and this will be x prime x squared here, the y. That's the only transformation that the formula has. Now x prime will be 1/2 x to the minus 1/2 here. And so when we plug this in here, this transforms in 1 over 4 x to the minus 1. Sorry, x to the minus y. Y to the minus 1. All right, and again, this is another substitution case. U is equals 1 plus 1/4 of y, and du is just 1/4 dy. So this integral is 4 times the square root of u du, and we're gonna forget for a second about the limit of integration to go back to the original variable. Then this is 2/3 or 8/3 really, with everything, of u to the 2/3 plus c, or uh, 8 over 3 1 plus 1/4 y to the 2/3 between 0 and 4. And so now we plug in 4, and of course we get a divided by 3 by 2 to the 2/3, and then I plug in 0 and in Sierra this becomes 1, so this is just 1 here. Now we can kind of see what happens numerically, just to find out what kind of number is that. So we get this is 1.56. And that will be the arc length for that specific function. By the way, now that we're using Desmos, in particular, we can check what are the curves that we're actually seeing. And if you're wondering what are the specific curves, and you can go with x equals the square root of y, and then you can say, well, we're moving between 0 and 4, so you can put this here, or just say y is bigger or equal than 0, and here less or equal than 4. And so this actually showcases what is the curve that you're measuring. You're measuring the length of this curve over here. Okay? You can do the same thing for all the others. Okay, so this is the end of section 8.1. Now we're going to transition to do kind of the same thing, but from the point of view of not length, but what happens when we take a surface of revolution and we want to actually compute the surface.